This is our presentation on evaporation. We are the Calc-Aholics. I'm Kyle.
My name's Ivan.
I'm Manny.
I'm Mike.
So a little bit of background and intro to what we are going to be presenting on. So what is evaporation? Evaporation is the process of converting a liquid into a vapor or gas at the surface of the liquid into the surrounding environment. The rate of evaporation is the amount of volume lost per unit time over a certain surface area of the liquid that is evaporating. Evaporation is a complex process that is affected by many variables such as temperature, humidity, what fluid is being evaporated, and the air pressure surrounding the liquid. Each of these factors can change how quickly the evaporation occurs, and this is known as the specific rate. The cross-sectional area at the surface of the liquid will also have an effect on the specific rate of evaporation. And in these experiments, we will be looking at the evaporation of 91% isopropyl alcohol solution with water in 6 different scenarios. These scenarios will be different in terms of the size of the dish holding the liquid while it evaporates. The liquid will be in Petri dishes, so the area will stay constant during each of the first experiments. And then at the end, we will also be evaporating the liquid in a cone. So as the liquid evaporates, the cross-sectional area will decrease. The evaporation of pure water will also be calculated, which will be helpful in calculating the evaporation rate of pure isopropyl alcohol. So the purpose of this experiment, in the experiment, data is collected on a 91% isopropyl alcohol solution with water in various containers. The data was collected using a digital scale. The data collected by the scale was automatically uploaded to a file, which was then copied into Excel. The data was collected over a 30-minute period with measurements taken 4 times a minute. Some collection times were longer, some were shorter, but these variations will not have an effect on the results. The evaporation rate of the liquid in a cone will also be looked at. Since the diameter of a cone decreases as you go down the cone, the liquid evaporates. As the liquid evaporates, the cross-sectional area will also decrease. This is important to investigate because it proves that the area has an effect on the rate of evaporation, where the first set of experiments in the Petri dishes do not incorporate this as a variable.
So for this part of the activity, we are given 3 different scenarios or models in which we have to find the rate of evaporation. The first one we are given the equation negative K multiplied by VT, in this case is a volume at specific time squared. In this case, V sub 0 at time is equal to 0 is our V sub 0, which is our initial value. This equation is not the worst. However, this equation does not work well in determining the evaporation rate. Even though in this equation, you are trying to determine the evaporation rate by using the specific volume, the volume is being squared, meaning the values are increasing drastically. This equation would not work due to the rapid increase in values. The pros in this equation is that specific volume is supposed to be used at a given time. However, it does not take into account of the cross-sectional area and is not linear because in this case, the specific volume at specific time is being squared. For part 2 of the equations, we are given K, which is once again our rate of evaporation, and A sub T. In this case, this is a cross-sectional area of, in this case, we are given Petri dishes and covers, which are 6 samples. And similarly to the last one, we are looking at the specific volume at time is equal to 0 is our initial volume. The pros in this one, it takes into account the cross-sectional area and is linear because nothing is being squared and everything is kept constant. The only con in this equation is the idea that both rate of evaporation and the cross-sectional area will be constant, given only one initial value. This is considered the worst equation. This equation is considered to be the worst based off the idea that volume is not used and cross-sectional area is constant. Based on the calculations, the cross-sectional area will be constant throughout, meaning you will not be able to calculate the rate of evaporation of the liquid or alcohol. This would be considered the worst out of the three, given based on the idea that the key idea is to determine the rate of evaporation of the alcohol. The final equation that is given, in this case, we have the negative K, which is our rate of evaporation, similar to the previous two equations, and V sub T, which is once again the specific volume at a specific amount of time. Volume at rate equals 0, at time is equal to 0, is equal to our initial volume. Similarly to the first equation, K is a rate of evaporation, which is constant throughout and is what we will be solving for later on. It is linear in a downward slope, meaning that it is easy to find rate of evaporation. The only con is that it does not take into account into cross-sectional area. Based on this equation, it is considered the best equation out of the three given equations, based on the idea that the slope is linear of the rate of evaporation and it can be determined. When the points were recorded and graphed, the rate of evaporation, which is in grams per minute, was determined as 0.009 for small dish, 0.027 for medium dish, and 0.0619 for large dish. These values will soon be evaluated later in the presentation and will determine the rate of evaporation. For the next two, we had to create our own equations that best suits, first off, how it would reflect on how we could get rate of evaporation, and second, which equation would be considered the worst. In this case, we looked at the mass at specific time of each dish and cover. K is our rate of evaporation, once again, throughout. It is considered to be linear and no calculation was needed because we weighed each Petri dish and cover, and mass would be determined based off the following values. And the only con in this situation is that it does not take into account of the cross-sectional area. This equation is considered the best out of the two that we evaluated, based on the fact that it's given us a negative relationship and it will be able to determine the rate of evaporation. Our final equation that we would evaluate to is negative K, which is finally our rate of evaporation, and P sub T, which is our density at specific time. All are evaluated at specific volume is at time equals 0, gives us our initial volume. The pro of this is the idea that rate of evaporation is constant, which is K. However, this will require further calculations, causing error within the graphs and plots. This will also be linear. However, it will be in the opposite direction based on the fact that volume is going in a negative slope, mass is going in a negative slope, and negative number divided by a negative number is a positive, meaning that it will lead us to a positive slope. This is considered the worst equation based off the fact that it does not give us the correct rate of evaporation and will not be used in this experiment. For this activity, we will be determining which Petri dish or cover is the best and will be used throughout this experiment. In this activity, we will look at the large Petri dish cover to model the rate of evaporation. The reason for this is the idea that based on the third equation, which states that V sub T is equal to negative K times the specific volume at time, The reason for this is the idea that based on the third equation, which I just stated, the correlation of the evaporation rate is almost, if not perfect, to the relationship of the specific volume and time. The purpose of this activity is to determine which is the best to determine the rate of evaporation. And like I said, the large Petri dish cover is the best one. Based on the data tables that were calculated and measured, the left table represents the measured values of the dishes with the alcohol. In this case, the large Petri dish had the highest mass of 85.91, including the alcohol. The right table, when plotted, will represent the rate of evaporation with the use of time and mass. This would determine the rate of evaporation based on the correlation and slope of the graph when plotted. Finally, based on the data recorded in the graph, it can be concluded that the graph is representing the rate of evaporation. The correlation, which is represented by R squared, is almost, if not perfect, to 1, which means it's an accurate representation of the data that was given, giving us a constant linear slope. Based off the slope, which is negative 0.1043, it can be determined that it's a slope and conclude that's the rate of evaporation.
For this activity, we are trying to find the rate of evaporation of water, and in the experiment, we collected data in a large Petri dish that will be performed on a digital weighing scale. And the model that we used was one of our own models that we came up with, which was the negative K, which is the rate of evaporation multiplied by the mass at a specific point of time. And using this equation, we are observing this Petri dish in a span of over 7 hours and recording at specific intervals the loss of mass in which the Petri dish has lost, basically. Next slide, please. And in this data chart, you can see that the loss of mass that the Petri dish and the digital scale has given us is very minimal at over time in over about 7 hours. And in the graph, you can see that the slope of the line is it's almost horizontal, which means there's a very little change in loss of mass. And we found out that the rate of change, the rate of evaporation turned out to be negative 1.6 times 10 to the negative 4th grams per second using our own mass equation. And we were able to verify that in the Excel spreadsheet that the data was taken from, in which that the rate of evaporation was close to negative 2 times 10 to the negative 4th. And now that we were able to find the rate of evaporation of pure water, we also found the rate of evaporation of 91% isopropyl alcohol and water solution, which was negative 0.143 grams per minute. And we converted that into the same units as we calculated for the rate of evaporation of water, which turned out to be about 0.00174 grams per second. And our goal was to find the rate of evaporation of pure isopropyl alcohol, which means it's 100% an isopropyl alcohol solution. And we used the rate of evaporation of water and the rate of evaporation of isopropyl alcohol. And we multiplied the rate of evaporation of water by 0.9, which is 9% of 100% of the solution. So we subtracted that from the isopropyl alcohol, and we received a data value of 0.00172 grams per second as a rate of evaporation of pure isopropyl alcohol.
So in this experiment, we used a conical funnel. In the conical funnel, the bottom of the funnel is sealed and it is supported by cardboard cutout resting on a beaker lip. The apparatus with the petri dishes was similar, like my teammates explained, with the petri dish in place of the beaker and its contents. So in this experiment, we explored the evaporation rate of 91% isopropyl alcohol. And the conical funnel that was used was at an angle of 60 degrees, formed by the oblique lateral edge and the horizontal when the funnel was stood upright. The diameter across the top of the funnel was 9.8 centimeters. This apparatus had an effect on the cross-sectional area because the diameter of the funnel decreases. Next slide, please. So this chart shows a part of the data collected over time to measure the rate of evaporation. We measure the time in minutes, which was the independent variable, and the dependent variable was a resulting mass of the isopropyl alcohol in grams over time. So over time, the mass can be seen to be decreasing, showing the evaporation in effect. Next slide, please. So after plotting the data, we found the relationship between the time and mass of alcohol. We then created a model based on the data, which shows the evaporation rate with the new apparatus. The model we found was y is equal to negative 0.09982x plus 177.63. So we found this to be pretty accurate because it's showing us a negative linear relationship. So think of this as the y equals mx plus b equation, which we have seen various amount of times. In this experiment, the m value is negative 0.09982, which is showing us the rate of evaporation, which is at a negative and it's linear. I find this model to be very accurate because it's very close to the Excel spreadsheet that was provided to us. Next slide, please.
So in conclusion, after completing the experiments and analyzing the results, we can take away some valuable information. We learned that what variables are necessary to calculate the evaporation rate, what the evaporation rate for a 91% isopropyl alcohol solution is. We also calculated the evaporation rate of pure water and used that to calculate the evaporation rate of the 91% isopropyl alcohol. And that was used to find the evaporation rate of pure isopropyl alcohol. The effective surface area was also investigated by evaporating the solution in a cone.
Thank you for watching. Hope you enjoyed. If you have any information, click the link below. That is our Symbol Lab link where all the data was collected and recorded, including graphs, more information about this information, and the questions that we had to look at. Thank you for watching. I hope you enjoyed.